Welcome to presentation 16. The subject for today is going to be the integrated circuit, I2C. That's a serial protocol, serial communication protocol. The I2C belongs to our layer 2 architecture. The agenda for today will be as follows. I'm going to give you some background on the I2C. I'm going to give you an explanation on how to set up the register to configure. I'm going to develop the I2C framework. And finally, we'll go through a couple of sample programs. So the I2C uses two wires to communicate. One is the SDA, the data line, and the other one is the clock line. These two wires are shared by all the devices on the bus. This is a master-slave architecture. One device, the master, controls the communication, while the other devices, the slaves, responds to the master. And later on, I'll explain how a device becomes the master. Now, the master needs to communicate with all the slaves. To make this possible, each slave device has a unique address. So the master can communicate with a specific device without interfering with others. So the master knows the address of these three slaves, and it can communicate separately with each of them. Now let's look at the different transactions that can happen on the I2. So basically we'll have a write and a read. A write is when the master sends data to the slave. A read is when the slave sends data to the master. So let's start with the writing sequence from the master standpoint of view. So first the master sends what's called a start message. Next it sends another message containing the slave address plus the write commands. So basically which slave it wants to communicate, and it's telling it this is going to be a write transaction. Next, the master starts sending the data. Now, the master will continue to send data until all the data has been transmitted. Now, once all the data has been transmitted, the master has a choice to either stop everything or transition to a read sequence. So in the case it decides that it's done, then it sends the stop message. Now if it wants to continue a transition to read, then what it does, it sends what's called a repeat start message. And at that point we go to the sequence, to the read sequence. So let's look at the read sequence from the master standpoint of view again. So first thing the master does is sends what's called a start message. After sending the start message, it sends the slave address plus read command. Then the master starts reading the data, and it continues to read data until all the data has been read. Next, the master has to decide whether he wants to transition to a write sequence or wants to stop. If it decides that it's done, then it sends what's called a stop message, which basically is releasing the bus. Now, if it decides that it wants to transition to write, then it sends a repeat start message. And then we go to the sequence as before. Now let's look at it from the slave standpoint of view. So the slave is just sitting there waiting for a command. When it gets from the master the request to write, then the slave gets ready and starts receiving the data coming from the master. Now it continues to receive data until all the data expected has been received, at which point the slave is going to expect to get a repeat start or a stop. If it gets a repeat repeat start, then it goes to the read sequence. If it doesn't get the repeat start, then it just goes back to wait for a request from the master. Now let's look at the read sequence. So again, the slave is just sitting there waiting until it gets a master request to read. That means it has to transfer data to the master. Then start transmitting the data. And it's going to continue to transmit data until all the data has been transmitted. Next, it's going to wait to see whether it gets a repeat start. If it doesn't get a repeat start, then it just goes to continue waiting for from a request from the master. If it gets a repeat start, then it's going to transition to a write sequence. Now status code. Every time I show that something happened from the master set the stars or so forth and so on, the way that the master or the slave knows that the sequence was successful is by monitoring status codes. So the microcontroller provides various status codes in the TWI status register. That's where you go to read the status code. Each code corresponds to a specific state in the communications. These status codes allows for the monitoring and control of communication flow. They make it easier to debug and manage I2C interactions. Now here I'm showing some of the codes, and I'm just showing to show you get an idea of the volume of the code. This is going to become, when I go through the flows and the example programs, this is going to become very evident the importance of this code. For example, a 08 would mean that the start command was sent, it was successful. The code 18 means that the slave plus write has been transmitted and that the slave acknowledged it. So also the slave has some status codes to know that its transactions have been successful or not. And then finally we have some status codes which are miscellaneous. So I want to go in more detail through the data flow, but this time showing the status codes. So I'm going to show you separately the flow sequence for the I2 writing and for the I2 reading. So I'm going to explain the slave address plus write and slave address plus read flow. So let's start with the slave address plus write. So the master, it's going to start the operation by sending the start message. Now, after sending the start message, the master is going to go and is going to monitor the status code. When the status code is equal to 08, that means that the start command was transmitted successfully. Once that happens, the next step, the master is going to send the slave plus write command. After sending this message, the master is going to monitor the status register until it gets a code 18 hex, which means that the slave address plus write was transmitted successfully and acknowledged was received from the slave. After that, the master is going to start sending data. Every time it sends data, it's going to monitor the status code until it gets a code 28 hex. At that point, it knows that the data was transmitted successfully and they acknowledge receive. And it's going to continue to do this until it has transmitted all the data, and at which point it's going to send the stop command, which releases the bus. So now let's look at this operation from the slave point of view. So a slave, it just sits monitoring the status register until it gets a hex 60 code. When it gets that, it knows that has received its own address with a write command. At that point, what it does is starts monitoring the status register again, and when it gets a code 80 in hex, it knows that data has arrived, it's been acknowledged, and it goes and gets that data. After getting that data, it goes back to continue to monitor the status register, and every time it gets a code 80 hex, it goes and grabs the data. And it's going to continue to do this until the bus is released. Okay, so now let's look at the slave address plus read. So again, the master will start the transaction by sending the start command. After sending the start command, it's going to monitor the status register until it gets a code 08. Once it gets this code, it knows that the start command was transmitted successfully. And the next thing it does is sends the slave plus read command. After sending this command, it's going to go back to continue to monitor the status register. When the status register is 40, that means the slave plus read command was transmitted successfully and acknowledgement was received. At that point, what the master is going to do is going to start monitoring the status register, and every time it gets a code 50 hex, it knows that data has arrived, so it has to get it, and it also knows that the data was acknowledged, I should say. Now, it will continue to do this until it has received all the data that is expected. And at that point, it's going to send the stop command, which releases the bus. Now, let's look at this from the slave standpoint of view. So a slave will, from the start, is going to monitor its status register until it gets an A8 hex, alpha 8, which means that it has received its own address with a write command. At that point, the slave will start transmitting data. Every time it transmits data, it's going to wait for the and monitor the status code until it gets a B8, Bravo 8, which means that the data was successfully transmitted and acknowledged by the master. So it's going to continue to do this until it gets the stop, at which point the bus will be released. So this gives you a good idea for the slave address plus write flow and the slave address plus read flow. So now let's look at a different flow. This time we're going to be looking at the combined reading and writing sequence. So this is more what it would really happen. So you would send a message to the slave requesting certain type of data, and then send a repeat start at the point the slave starts sending you data. Here, this graph shows the read and write sequence. So what we're going to do in this scenario is we're going to the master is first going to request to write data to the slave, and after it's written all its data, it's going to request that the slave starts transmitting data back. So let's get into the details of this transaction. So let's start with the master. So everything gets started when the master sends the start command. After the master sending the start command, it's going to wait till it can get the 08 code. At that point, it knows that the start command was transmitted successfully. So the next thing it's going to do is going to send the slave plus write command. After sending the slave plus write command, it's going to wait until it gets a status code 018. That 018 means that the slave got the slave address plus write command and it acknowledged it. At that point, the master is going to start transmitting data. Every time it transmits a piece of data, it's going to go to the status register and it's going to wait for a code 28. A code 28 means that the data that's sent, it was received by the slave and was acknowledged. So then it's going to continue to do this until it has transmitted all the data, and at that point it's going to send the start command. Now I would like to stop here for a minute and explain something. This start command, which is the second time it transmits it, it's called the repeat start command. And the first time it sent the master the start command, it expected to get a code 08, meaning that the transaction was successful. Now, when it sends the start command for the second time, what it expects to get is a hex 10, which means that the start command, which is called now a repeat start, was successful. So after it gets the repeat start code, status code for a 10, that means that the start command was successful, and now it's going to transmit the slave address plus read. After transmitting the slave address plus read, it's going to monitor the status register until it gets a hex 40 status, which means that the slave got the address plus read command and it acknowledged it. At that point, the master is going to monitor the status register until it gets a hex 50. When it gets hex 50, it knows that it got new data from the slave and that it had already acknowledged it, so it can go and get the data. After getting that data, it's going to monitor the status register, and every time it gets a status code 50, it's going to go and grab the data. Now it's going to do that till it gets a code 58. A code 58 means that data has been received but with no acknowledgement, which means that's the last piece of data it's going to get. So the master will go and get this data not acknowledged, and then it would send the command to stop, which is going to release the bus. Now let's go through the transactions, but from the slave point of view. So the slave is sitting there monitoring its status register till it gets the code 60, which means that it got its own address plus the write request. So after getting that command, the slave will start monitoring again the status register, and every time it gets a status code 80, it knows that it had gotten new data and it has acknowledged it. So it will go and get the data and then go back to continue monitoring the status register. So it's going to continue doing this until it gets its own address plus write command, which is going to be when it gets the status code alpha 8. At that point, it's going to start transmitting data. Every time it transmits a piece of data, it's going to go and it's going to monitor the status register till it gets a Bravo 8, a B8 status, which means that the master got the data and it acknowledged. Now, when the slave has the last piece of data and it's going to send it, this time it's going to send it with a not acknowledge. So what it's going to do is going to wait for a status code to get Charlie 0, C0, and at that point that's going to signify that it's going to send the last piece of data has been transmitted, and it would expect that after that the bus would be released by the master. So this gives you a transaction where you're using the write and read sequence. And the idea is that when you send, you first would, a transaction, you would first send the write command requesting the data that you need and what data you need, and then the slave would actually send you the data. So now let's talk about the master, how you become a master, how you decide who's going to be the master. So when the current master sends the stop condition, the bus is considered free, and any device can attempt to become the master by sending the start condition. The I2C protocol does not have a predefined priority system. If two or more devices try to become the master simultaneously, the I2 protocol uses an arbitration process to resolve the conflict. Devices monitor the SDA line while transmitting. If a device detects that the SDA line is low when it is expected to be high because another device is driving the line low, it knows that another device is also trying to become the master and withdraws from the arbitration process. The device that successfully transmits the address without detecting any conflict on the SDA line wins the arbitration and becomes the master. So if you get on the SDA on the line and you send the address plus read by write successfully, then you know that you're the master. Otherwise, back off. A priority system can be created at a higher level in the system design. For example, once the bus is free, the device can be programmed to wait for a random amount of time or assigned amount of time before attempting to take control of the bus, reducing the chance for collisions. So when the bus is free, you wait a predetermined time or a random time and then you get on the bus. And the idea is that not two devices are going to wait for the same time, or you pre-assigned how long each device have to wait, which in essence you are giving priorities. So let me explain you the registers. So we have a TWBR, sets the speed of the communications. Then we have the WSR, shows the status of the operations and clock prescaler. That's where you get all the status that we've been talking about. Holds the slave address for the microcontroller. So you put the slave address here, and that determines the address of the slave. Stores data to be transmitted or received. That's the TWDR. The TWCR controls the operations, and the TWAMR masks the address, allow multiple address recognitions in the slave mode. So let's look at each of these registers in detail. So we're going to look at two first. That would be the TWBR, which defines the speed of communication, and the TWSR that sets the prescaler. Okay. Calculating the value for the TW bitrate register. That's the name of the register. Now, how do we determine the desired frequency? It is common that the transmission will be at 100 kilohertz or 400 kilohertz. That's the typical speed that you would use, one of those two on your bus. Now, based on the frequency of the desired frequency, you have to put in a value on the TWBR register. So what value do you use? So you have to calculate it. It's going to be equal to your processor speed divided by your selected speed for your bus minus 16, all this divided by 2 times the prescaler. So let's see what this means. Now, this prescaler, so we know this value, 16 megahertz. We know this ACL can be 100 kilohertz or 400 kilohertz. We know this is 2, and then we need to select the prescaler. So the prescaler can have a value of 1, 4, 16, and 64. That's the ones you have a register, you put in a bit, set of bits, and that's the value you can select. Now, how do you go about selecting this prescaler? Now, the TWBR, this register, it's an 8-bit register. Therefore, we need to select the value that will make the TW calculations less than 255. So basically, this number can be as high as 255. So what you do is you make your calculation, and if your calculation is greater than 255, then you put a divided by prescaler to make it fit in this register. So let's do a calculation. Now we're going to do this calculation using the prescaler 1 to start. If the result is 255, less than 255, then we calculate the number for the TWBR register. So for the prescaler to be a 1, is basically you have to set these 2 bits to 0. So let's go ahead and do the calculation. So for a 100 kilohertz frequency, so we have 16 megahertz divided by 10 kilohertz minus 16, everything divided by 2 times 1, the prescaler is 1, we get a value 72. So in this case, if we want to use a 100 kilohertz, then no problem, we just use prescaler 1. Now let's do this same operation, but for using a 400 kilohertz. And again, here we have 16 megahertz hertz divided by 400 kilohertz minus 16 divided by 2 times 1, and that gives us a value of 12. So that means we can use a prescaler of 1 for our microcontroller, which is 16 megahertz clock. So next, let's look at the TWAR, which holds the slave address, and the TWDR, which stores the data to be transmitted or the data we received. Now the TWAR is an 8-bit register. The first 7 bits holds the address, and the last bit is going to be a 1 or a 0, which is set. If it says a 0, it's for a write command, and if it's a 1, it's a read command. So before I was talking about sending a address plus write command or address plus read command after the start command. Well, this is how you set it up. First 7 bits is the address, followed by 0 for a write command, and 1 for a read command. So here we have an example. If we have a 7-bit address, which is hex 1D, and the master wants to send a write command, then what it does, it takes this value, which is 01111010, 01111010, and adds a 0 at the end, which would be hex 3A. If it wants to send a read command, then it's the same thing, except that the last bit is a 1. So write, read, and the address is exactly the same. Now for storing data, for transmitting and receiving. Now wait. So what you do when you're going to get or you send data, you wait in a polling loop, continually checking status flag in a while loop to determine if the request either read or write has arrived. Or we can use interrupts that will trigger when a request has arrived. So basically what I'm trying to say is that when you transmit data or you receive data, basically you get into a while loop, monitoring a flag, or you set the interrupts that are going to be triggered when you get some kind of a transaction request. So let's look at the TWCR control register. So we have the interrupt flag. It gets set every time an operation occurs. So we can monitor to see if the flag got set if we're in a while loop. Next we have the TWA, which controls whether an acknowledgement should be sent or not after receiving a byte. So once you receive a byte, you can decide whether you're going to acknowledge it or not. Now this is the start condition. I mentioned that you need to start the transactions on the bus by sending the start condition. You set these bits and the start condition will be sent. Then you have the stop condition to release the bus. Then you have a write collision flag. When you have a collision in the bus, two devices try to get at the same time, you get that flag set. Then this flag is to enable the I2 transactions, and then the TWI is to enable the interrupts. So let's look at the INT interrupt flags. The TWI INT flag is set when one of the following conditions occurs. So you have completion of the start condition, completion of the stop condition, completion of the data transmission reception, completion of an acknowledgement, completion of an address transaction. So basically what I'm trying to show you here is that when these flags get set, then you're going to need to look at the status code and try to figure out which of these operations happen. Now let's look at the mask address register. The slave device will only respond to exact address set in the TWAR register. By setting a mask, you can make the slave respond to a range of address. So let's see how we do this. For example, suppose the slave address is 50 hex. If you set the TWMR to E0, the slave will ignore the bits where the TWMR has a 1. So what do we have here? So 2, 4, 6, 7. So these are the address of the slave. So it's going to ignore its first 3 zeros because we have 3 ones. 2, 4, 6, 7. 1, 2, and 3. So it's going to respond to an address 0101. So this means that the slave will respond to any address where the first bits are 0101. So the slave is going to respond to a address 50, 51, 52, 53, and so on, because it only looks at these 4 bits of its address, or thinks that its address is 0101. Using the TWMR register to address masking allows you to broadcast a single message to multiple devices simultaneously, making it an efficient way to control synchronized group of devices. So you can address all these devices at the same time. The one that has address 50, 51, 52, and 53 by setting in each of those devices a mask of 0E hex. So now let's get into our framework. So we're going to review the data sheet as usual. Then we're going to develop our framework by creating our traceability tables. And from those tables we extract the code. So let's look at our data sheet. Before we put together our framework, we're going to review our data sheet. The data sheet contains all the information we need for programming the microcontroller. Now let's go to the section that covers the two-wire serial interface. Now from here we're going to jump to the register description. The first register that we have is the TWI bitrate register. With this register, we control the data rate transmission. Next, we have the status register. With this rate, we're going to control the what prescaler we're going to use, and also we can read the TWI status bits. So all the status bits would be contained in this register. Next we have the TWI slave address register. This is where we're going to place the register of the slave. Next we have the TWI data register. By accessing this register, we can read or write data that's going to be transmitted. Next, we have the TWI control register. In this register, we can read the flag. Next, we can enable, if we want to transmit or not, acknowledgement. We can send the start condition or the stop condition. We can check if there was any collisions. This is where we would enable the TWI and also enable interrupts. And finally, we have the TWI address mask register. This register will allow us to transmit a broadcast message. So anyhow, with this, I'm giving you a global idea of the register associated with the TWI, or which is synonymous to I2C in this case. So let's go and start developing our framework. Okay, so let's start with putting together our table. So here we have the information we extracted from the data sheet, and what we're going to do is we're going to write our code to manipulate those bits. So I have the code that I've developed, yes, by getting the information from the data sheet. Okay, this is what that the framework looks. But also, in addition, I added the code for the start transmitted, repeat start, slave plus write transmitted acknowledgement. So all the codes, the status codes, I also add them to this framework. So the framework will be implemented as a framework TWI.h. The source code is generated by extracting the code from the column code, associating the names of the status code. So I also developed for the status code. Now, to prevent any naming conflicts with existing development environment, the parameter names have been modified by adding an X in front. So all this work that I have here, usually you can get it in the environment, but in any case, if you don't, you know how to do it. And finally, as a side effect, we have created a traceability to our source code back to our data sheet. So we have our source code, and every time we use one of these parameters, we can go back, we know where it came from, and we have a table that shows exactly where we got it from. So now let's start with our sample program. So I have two sample programs. In the first one, we use the while loop, and the second one, we're going to use the interrupts. The interrupts are actually a more realistic way of doing this. So let's see what the master is going to do. So this is our master, and this is how the two processors are going to be, microcontroller are going to be hooked up to the wire. So that would be the SDI is going to be PC4 port, and SCL is PC5 port. The same is here. That's something that you know. And the PV1, that's where we're going to hook up our LED. So the CDI square as parameters as follows. The speed is going to be 400 Hertz with a scalar of 1. We already figured that one out. The slave address is going to be 10 hex. Then what the master is going to do is going to send the start command. Then it's going to transmit the slave address plus write request. Next is going to request the slave to turn an LED on and off 10 times. For the on command, it's going to be 0F hex. The off command is going to be F0 hex. And finally, it's going to send a stop command. Now, what is the slave going to do? The slave address is going to be, of course, 10 hex. It's going to receive the message from master. If the message is 0F, it's going to turn on the LED. If the message is 0F, it's going to turn it off. And then when the stop command is received, it's just going to transition back to waiting. So let's start by looking at the master program. I will start by giving you a global view of the program. So we have a routine to initialize the I2C, a routine to transmit the start command, a routine to transmit the repeat start command, a routine to transmit the stop command, a routine to transmit data, a routine to receive data. Then we'll have a routine that's going to transmit the slave address plus read. We'll have a routine that's going to transmit the slave address plus write. And then we have the main program, which is going to initialize whatever needs to be initialized, and it's going to send the command and then send the data for the slave to turn on and off LEDs. So let's get into the details. So this first routine, they need I2C. What it does is it sets the scalar and also calculates the value of the TWBR. Next, the start routine. What it does, it sets the bit on the TWCR to enable the transmission of the start. So what it does is sets to 1 the TWINT bit, which is resetting the flag. It sets to 1 the TWSTA bit, which is the one that generates the start condition. And finally, it sets the TWEN to 1, which is the one that enables the I2C. So this is going to send, this line of code is going to enable sending the start command. Then next, what it does, it waits for the command to be successful. And it knows the command was successful because the flag, the TWINT flag, gets set. And also it gets the acknowledgement, which is hex 08. So those two while loops are doing that. So let's go to the next routine, which is the WI repeat start. So it's basically a repeat start is basically sending a start for the second time. So again, we manipulate the TWINT bit, the TWEN, and the TWSTA bit, which are we always need to reset the flag, enable the I2C, and generate the start. Next we have the TW stop. Now this routine is going to send the stop command. So to send the stop command, you need to manipulate the TWINT, TWEN, and TWSTO bits in the TWCR register, which is basically setting the interrupt flag, resetting the interrupt flag, enabling the I2C, and then sending the TW STO, which is the staff condition. Then after executing this line, we wait to make sure that everything was successful. Next, we have the transmit data. To transmit data, what we do is we place the data in the TWDR register, and then we manipulate the bits as before on the TWCR register, which be manipulating the TWINT, which resets the flag, and manipulating the TWEN bit, which is the one that enables the I2C. After we transmit data, what we do is we wait for the data to be transmitted. Next, we have the received data with acknowledgement. So again, what we do, we manipulate the bits in the TWCR register, which are the bit, the TWINT, the interrupt flag, the TWEA, which is the enable acknowledgement, and then the TWEN, which is the enable the I2C. After we do that, then we wait until the TWINT flag gets set. Once that gets set, that means that the data has arrived. So we grab the data from the TWDR and return it to whoever needed the data. Next, we have the transmit plus read command. So to do this, we need to send the slave address followed by a 1, which means the read. So we place the slave address in the parameter data. By the way, the slave address was set up here to value 10 in the defines. So put the slave address into the data parameter. Next, I shift everything left one place, and after doing that, I place the 1 in bit 0. So what we have, so data is the first 7 bits are the address, and the last one it's a 1, which is the write command. Next, I place the data into the TWDR register and manipulates the bits in the TWCR, which are the TWINT to reset the interrupt, and the TWEN, which enables the I2C. After doing that, I wait for the transaction to take place. So after this while, the transmit plus read command has been transmitted. Now let's look at the transmit plus write command. So this is going to be fairly similar. So I take the address and place it to data parameter. I shift everything left, and then when I shift everything left, the last parameter is going to be 0, which means it's going to be a write command. And then I place this into the TWDR register for it to be transmitted. And then for the transmission to happen, I reset the interrupt flag parameter in the TWCR register, and then I set to 1 the TWEN, which is enabling the I2C. And finally, I go to my while loop, where I'm going to sit here and the transaction is completed. So now let's go to the main program. So the main program, first thing it's going to do is going to initialize the I2C. Then it's going to transmit the start command, followed by the by transmitting the address plus write command. Now once you've done that, now the slave is waiting for the data. So what I want to do is I want the LED to come on and off for 10 times. So I accomplish this as follows. So my loop is going to go from 0 to 21. 5 times on, 5 times off. So that's going to give, 10 times on, 10 times off. That's going to make it on and off 10 times. So I transmit the input data, which has been set to off to start. Then input data is equal to not input data, which is going to turn it on. And then we wait 500 milliseconds. And we do this 20 times. After sending the command to set the LED on and off for 10 times, we send the stop command and we are done. Okay, so now let's look at the slave part of this program. Okay, so I'll start by giving you a global view of the program. So we have an init ports routine to initialize the ports for the LEDs. We have to initialize the I2C. We have a routine to transmit data, routine to receive data. And then we have the main, which is going to be responsible for initializing whatever needs to be initialized, and also for turning on and off the LEDs. So let's get started. So first, we have to initialize the ports where our LED is set to output. So I do that by setting the whole register to FF, all the ports B to output. Next, I have to initialize the I2C. The only thing we need to do for initializing the I2C is we need to place the address of the slave. So basically we have the slave address and we shift everything to the left because the first 7 bits of the TWAR has the address. And the address again is set up here in the define as hex 10. And then we also have the parameters for the light on and light off. Now let's go to the transmit data. So for transmitting data, what we do is we place the data in the TWDR register. After that, we manipulate bits in the TWCR register to make all this happen. So what we need to do is set the TWINT, which actually should be reset the flag. Next, we need to set the TWEN register, which enables the I2C. And finally, we need to set to 1 the TWEA bit, which enables acknowledgement. So after we do that, then we just wait for the transaction to take place. Next, we have the receive data. So what we do is in the TWCR, we manipulate the following bits. We reset the flag by placing a 1 in the TWINT register. We enable the I2C by placing a 1 in the TWEN bit. And finally, we set a 1 in the TWEA bit which is going to enable acknowledgement. So after doing that, we just sit and wait. When the flag gets set, that means that data has arrived. So we grab that data, which is going to be placed in the TWDR register, and we return it. So let's go to the main program, see what that's doing. So the main program, first thing is going to initialize the port. Next is going to initialize the I2C. Then we'll get into an infinite loop. So in the infinite loop, first we have a parameter receive data. And what it does, it waits for getting the data from the receive data routine, which would be the TWDR parameter. Once the parameter is returned, then it asks whether the request is for a light on, and if that's true, then it turns on the light, else it turns it off. And then it keeps doing this forever, just waiting for a command to arrive and then taking action accordingly. So what's going to happen is that it's going to get the command to turn on and off the LED 10 times. And that basically gives you an idea of what this routine is doing. Okay, so let's go to the next sample program. This sample program is going to be interrupt driven. It is more realistic of what really happens in the real world. So first, let's see what the I2 master is going to do. So let me go here to the schematics. So we have two microcontrollers connected to the bus, I2 bus. Both of them have an LED, and they are connected to the SDHC, both of them. So kind of giving you an upfront idea, the master is going to tell the slave to turn the LED on and off 4 times, and then the LED is going to tell the master to do the same. So the idea here is the master is going to send data to the send data to the slave requesting certain data, and the slave will get that data and see what the master wants, and then return the data requested. So let's look at the master. So parameter, the transmission rate is going to be 400 Hertz. Scalar is going to be 1. Slave address is going to be 10. So the master is going to transmit the start command, transmit the slave address plus write request, request the slave to turn on and off an LED 4 times. That represents the master asking the LED, asking the slave for certain data. Then the master is going to transmit the repeat start command. Next, it's going to transmit the slave address plus read request. If the slave transmits a 0F, the master is going to turn on an LED. If the slave transmits the F0, then the master is going to turn off an LED. If the slave transmits the 0FF, then the master knows that it's gotten the last piece of data and is going to stop, which releases the bus. Now what the slave going to do? Address is going to be 10 hex. Then it's going to listen for the start or repeat message from the master. Then it's going to listen for the slave plus write message and return acknowledgement. If the master transmits the 0F, then it would turn on the LED. If the master transmits the F0, then it's going to turn off the LED. Next is going to listen for its own address plus write message and return acknowledgement. Request the master to turn on and off an LED 4 times. At the completion, it's going to transmit a message containing the FF with a NAR acknowledgement. That means that it's done. That's the way the master knows that the data has all been transmitted. So let's start by looking at the master code. Okay, so let's start by giving you a global view of this program. So we have a routine to initialize port, a routine to initialize the I2C. We have a routine to enable and disable interrupts. We have a routine to transmit the start command. And then we have the main, which is going to do initialize whatever it needs to initialize. So let's continue. Now everything is going to happen here in the interface interrupt, should say, service routine. This interrupt routine has a switch statement, and in the switch statement it's going to contain the status code, which is what we're getting after each operation. And according to the status code, it's going to perform a function. So let's go back and look at the details. One of the items that I defined here is a data to send array. Now this array is going to have 8 elements. And it's kind of simulating that the master wants to send 8 pieces of data to start. So we're going to have a light on, light off, light on, light off, and so on in this array. So we also have the slave address here, and then the light on value, which is 0F, or light off, which is F0. So let's look at the init ports. Now this routine is going to initialize the port B, pin B1, where is the LED is connected. So we can, as an output, so we can turn on and off the LED. Now the init I2 routine, what it's going to do is going to set up the scalar, which is going to be 1. It's going to calculate the value of the TWBR for a 400 hertz data transmission, and also it's going to set the TWCR bits needed to perform the function, which is going to be, we need to clear the interrupt flag, we need to enable the hardware, we need to enable acknowledgement, and then we're going to enable interrupts, because this is going to be an interrupt driven program. Next we have the TW start, which is the routine that is going to send the start command. So what we do on the TWCR, we set the TW STA bit to 1, which is going to send the start command. And then to make things happen, again, we reset the interrupt flag, we enable hardware, enable acknowledgement, and then we enable interrupts. So now let's go to the main program. So what the main program is going to do is going to initialize the ports, initialize the I2C, enable interrupts, and finally it's going to send the start command. Once it sends the start command, the rest of the program is going to react to interrupts. So let's look at the interrupt service routine. So we have a switch statement, and when we add the TWSR to F8, that's going to extract the status code. So now we first send the start command that we already did on the main program. So as soon as you send the start command, you have to wait. There's going to be an interrupt that's going to be triggered by when the start condition was successful. That means that when the interrupt gets triggered, the code is going to be 08. If the code is 08, the next thing we need to do is we need to send the slave address followed by slave address with a 0 at the end, which means that we're going to get into the write mode, slave plus write mode. And to make this happen, what we do is we clear the interrupt flags. We enable the hardware, enable the acknowledgement, and we enable interrupts. After this happened, in the next time we get interrupted, we should get a case 18, which means that the slave plus write was successful transmitted and acknowledged receive. Next, what we do here is we're going to start transmitting our data, because after getting the 018 code, we know that the slave is waiting for our data. Now I put in a delay of 500 milliseconds, which is something that I do it by experimentation, and it worked fine. So I don't want everything to be so fast. So I'm sending one element of an array at a time. So my first question is, am I at the end of the array, which is the data length? And if the answer is no, then I need to send the data. So I put the data in the TWDR register, and after sending, I increment the index. Now, to make this operation happen, what I need to do on the TWCR is again, I need to reset interrupt, enable hardware, enable acknowledgement, and enable interrupts. Now, I'm going to continue to be interrupted with the case 28 until all the data is transmitted. Now, once all the data is transmitted, then I'm in the else case. That means that the index, the data length, the index is greater than the data length. So I get into the else. So what I need to do at this point, I need to send the start, which would be the repeat start in this case. I need to send the repeat start, but it's sent as a regular start. And so that's what I'm going to do here. And I set up my index to 0 because that's just something that I need, especially if I go back for some reason to this program. So to make the start command go, I need to set the interrupt flag. I need to enable the hardware. I need to send the acknowledgement, ensure interrupts are enabled, and then send the repeat start, TWST. So this would be the repeat start. So once I do that, then what I'm going to wait is for the status code that states that the repeat start was successful, and that's case 10. So once I get this, that means that the start command or restart command in this case was successful, then I'm going to send the command for the slave to read mode. That means that it's going to send me data. So I do that by shifting the address one place to the left and placing the last bit to 1. So to make this happen, again, what I need to do is I need to reset the interrupt flag. I need to enable hardware. I need to enable acknowledgement and enable interrupts. So once I do that, then I'm going to wait. The next time, I should say, I get interrupted should be a slave code 40, which means that the slave address plus write was transmitted successful and we got an acknowledgement. Once I know that, then I know that that I get ready to start receiving data, because I know that the slave has acknowledged that it's going to send me data. Okay, so the first thing I do is I'm here at the case 50, which means that there is data available. So I put the data into the received data parameters. And the first question I ask is this data equal to FF? Because that's the code that the slave is going to send me once it's transmitted all the data that it was supposed to. So if this is FF, that means that I'm done. So what I'm going to do is I'm going to set the stop condition, which is the TWCR, and the bit, I should say the TWCR, which is the bit TWSTO, is set to 1. Now, if this is not the final message, then the next question is this a light on or is this a light off? If it's a light on, I turn on the light, and if it's a light off, I turn off the light. And after doing these actions, now I have to set the system for the next command. So how I do that? I clear the interrupt flags, enable hardware, enable the acknowledgement, and enable the interrupts. So after all the data is transmitted, I'm going to get the F and everything's done. Then I also have a default, in which case for the default what I do is I get ready for whatever message is coming next. So I hope I've given you a good idea of how to work the transmission using interrupts. Okay, so now let's look at the slave portion of the program. Kind of to give you a recap. So what we're going to do in this case, the slave gets gets inputs from the master and turns on and off an LED, and then after that it sends messages to the master to turn its LED on and off, and when it's done it sends the command FF. Okay, so I'll start by giving you a global view of the program. So we have the array called data to send, where we're going to have 8 elements, which is the data that the slave is going to transmit to the master. And this simulates that the master has requested data, and this is the data being returned. Next we have the address of the slave, which is 10 and then the code for light on and light off. And then we have this number that represents the 400 Hertz that we want to use for data transmission. Now we have a init I2 routine which initializes the I2. We have a routine to enable interrupts, and then we have the main program. Now finally we have the interrupt service routine. This routine is going to take care of all the transmission, the writing and reading, and it's going to react to interrupt and also to status codes. So let's get into details. So the init ports, what this routine is doing is initializing the port B, pin B1 to output, because that's the LED that we're going to be turning on and off as commanded. The I2, the initialization of the I2, which is the init I2, what we do is we set the slave address. Next, we set the scalar to be 1, and follow by setting up the TWBR register. We need to do this calculation to set up the correct data transfer. And finally, to make things happen, as usual, we reset the interrupt flag, enable the hardware, enable acknowledgement, and enable interrupts. So this routine enables a global interrupt. Let's look at the main. So the main, what is it doing? It's initiating the initializing the ports, initializing the I2, and then initialize interrupt, and that's it. So now this program is going to just sit doing nothing until it gets a command from the master. And when it gets a command, we're going to have an interrupt. So in our case, what we expect is that the first interrupt is going to be hex 60, which means that the slave got for his own address a write command. So the next time it's going to get an 80, it has to be ready for receiving data. So the next interrupt, if there is new data, it gets a code 80. So it got a code 80, so it knows that the received data needs to be loaded with the data contained in the TWDR register. Now, if the data received is equal to light on, then it turns on the LED. Else, it turns off the LED. After doing that, it sets the hardware for the next statement, which is by setting up the resetting the interrupt flags, enabling the hardware, enabling acknowledgement, and enabling the interrupts. Then once all the data has been transmitted, what's going to happen next is we're going to get the repeat start. When the next interrupt is going to be the repeat start, because that's what the master is doing. So we get the repeat start here. So in this case, what we do is we set the we clear the flag. Next, we enable hardware, enable acknowledgement, ensure interrupts are enabled. Next time, after getting the repeat start, what we're expecting to get in the next interrupt is going to be the slave own address followed by the write command. And what that happens, then the slave knows that it's time to start sending data to the master. So first thing it does is puts a delay. As before, we do that to slow down things a little bit, and that's a number I got by experimentation. So the first question is, am I done? I'm going to be sending elements from a array. So I want to know, did I send all the elements or not yet? So if I haven't sent all the elements of the array, then I put the element into the TWDR and increment the index. So the next time I get to the B8, I'm sending the next piece of data. So I send the data, which is going to be an on or off command. Next, I set everything up for things to continue working. So that's the interrupt flag get reset, enables hardware, enables acknowledgement, and enable interrupt. So I'm going to be getting to B8 every time I send a piece of data until I've sent them all, which means the index is greater than the data length. At that point, what I'm going to do, I get into the else here. So what I do, first I set my index to 0, because when I want back, if I come back, I want that index to be 0. Next, I'm in the else because I've sent all the data. So the next piece of data that I'm going to send is the 0FF, telling the master that I'm done. And then I'm going to transmit that, and I'm going to send this a little bit different how I treat the TWGR in the last element. So I'm going to clear the flags, I'm going to enable hardware, but then I'm going to send a not acknowledgement. I'm going to set up the interrupt, I forgot, but then finally I'm going to send a not acknowledgement, which means that I don't include the send acknowledgement. So I leave that out. That means it's going to be a no acknowledgement. So here what I'm doing is setting the index to 0, sending the FF to the master, saying, hey, I'm done, and then I'm not requiring any kinds of acknowledgement because I'm done. And that's going to end up this program. In case there is a default code or something gets corrupted, then we ignore it, but we set up the hardware for the next message. So I think that gives you a good idea how this works using the interrupts. Okay, so we got to the summary. So today's presentation, I gave you some background on the I2C. I gave you some information on how to set up or configure the I2C registers. We put together the I2C framework. And finally, we went through a couple of programs, one using while loop and the other one using interrupts. So I hope you've enjoyed this presentation, and thank you very much.